Yes, we are starting. So, good morning, good afternoon, and good evening for the people across various parts of the globe. Welcome to the webinar organized by IEEE Joint Chapter Kerala. And today we have Professor, none other than Professor Blaabjerg with us. He's a full professor from University of Denmark, and he's the president of IEEE Power Electronics Society, and he's a well-known researcher, well-known worldwide researcher in many fields. And I invite our chapter chair, Dr. Bijana Kunju, to introduce the speaker of today. Bijana Madam, over to you.
Good evening, good afternoon, and good day to all people who have come across the world to here to one of the very special speaker for us. The joint chapter, this is history coming today with the IEEE Power Electronics President himself, Professor Frede Blaabjerg, speaking to us. It is indeed our pleasure to introduce the speaker. And of course, I welcome Professor to this function. It is indeed our prestigious occasion. And of course, it is my honor to introduce a speaker. I can say that if somebody calls for a creator for power electronics applications into renewable energy and electric vehicles, I would suggest that he is a synonym for that. He has been the person behind the whole creation of connecting the two things, which was never thought of as so easy. And he is the actual person who has created so many papers of real worth. And if you look at the citations of his works in IEEE transactions, the citations goes around 4,000 and 5,000. That actually gives the value of what he has done till now. To talk about him, he was born in 1963, got graduated in 1982, and then his MSc in Electrical Engineering and System Constructions in 1987, and his PhD in Modeling Power Electronic Components and Circuits from Aalborg University in 1995. And he has been with Aalborg since 1902 and is a full-time professor there. These are just a few things to talk about him. The other things that makes him different from all the others is that he has been the editor for the IEEE transactions on power electronics. He's a distinguished lecture program member of IAS as well as Power Electronics Society. He is currently and being the visiting professor of several other universities all around the globe. And to his remarkable achievement, we can quote to around 40 awards all over the world, if you look at. But of course, among them, we cannot forget to speak about the IEEE Edison Medal, which he won this year, 2020, the highest award that IEEE gives for a research. We are indeed, I want to congratulate him, and we are indeed very fortunate to speak to a person and listen to him also, who has actually won the Global Energy Prize for 2019, IEEE William E. Nobel Prize for Power Electronics Award in 2014. He became the fellow of IEEE in 2003. And if I try to continue with what all achievements he have made, we may not get enough time for the speaker at all. So it is indeed my pleasure to welcome you, sir, to this function. And we are so fortunate to have you this day. Thank you.
Okay, thank you. Can you hear me clear?
Yes, sir.
Yes, yes.
Perfect, thank you. What a nice presentation and introduction of me. That warms my heart, and I'm also very happy to have the opportunity for the Power Electronics chapter to give this presentation, and I'm very thankful to all of you who are volunteers for the Power Electronics Society, because without volunteering work from you, we will never have a power electronics society. So thank you very much for doing this, and I hope that you will continue with arranging things and also do networking, develop people so they become better and better in our field of power electronics. As it was said that maybe I have been active for many years in the power electronics discipline. That's maybe true, but I think we still have a lot of more to do. So you should just keep on working with this technology, and there will be so much to contribute with also for the country, for the planet, in order to create a sustainable environment in general around the world. So my topic this evening for you, I think most of you, is about one of the areas we have been working with for 10 years or so, and that has been reliability in power electronics. And let me just first, I go to this field. Let me just say where Aalborg is. This is Denmark. We are located here. So I have been in India maybe 4 or 5 times. So it's not that far to go to India. I think it's around 8-9 hours, dependent on the route from Aalborg, Amsterdam, and then to India. And Denmark is a small country, but Copenhagen we have here, and up here we have Aalborg city. And Aalborg University was founded in 74. A little bit characteristic of the university is that our students, they work in teams. So this is a little bit different compared with others. So they work in teams during their study program. And in that way, they work with problems which they try to solve in teams. And this is a little bit unique because then you learn to make a project and also be successful in a project. But a little bit about my department, where the university has 19 departments. The university have 23,000 students, and one of the departments is energy technology. And in this department, we look at power generation, transmission, distribution, use of electricity. But energy technology is more than electricity. This is also transportation, right? It's also where we consume a lot today in terms of fossil fuel and so on. And it's also thermal energy in order to cool or heat up houses and so on. So it's a complete system where it's not only electrical engineering. So yeah, maybe I just take one thing more. Here is that this department I'm coming from, we have around 120 PhD students, and in total around 300 people, where I would say a lot of activities are related to power electronics. And power electronics you can also see in this figure here. Because this is really shown in a lot of applications in terms of consumption, but also it's applied in electrical generation, it's applied in transportation, in this case here, where we both have the transportation in the car, a lot of power electronics, but we also need to charge the batteries, for example, if we are dealing with an electrical vehicle. But what I'll do today is I'll first speak a little bit towards reliable power electronics, and then I will discuss a little bit some different challenges we are facing in this area. But in general, we are using power electronics in a lot of application, from generation to consumption. And here are shown some different places where we are consuming a lot of electricity, and in between we are putting the power electronic topologies, which we can do in many different ways. And we have the components. We want to control the input-output, and when we have put the components together, of course, we also need to do some kind of control in order to have the performance we want to have. So when we talk about reliability, then of course we want to have a certain security that this equipment is operating in a certain lifetime according to the specifications we want to have of such one. And then we just, if we look at those applications here, I can ask the questions to you. If I was face to face, do you want the same lifetime on those applications here in terms of power electronics design? And I think you will tell me yes, maybe for the railway and for the house, we want maybe some of the same lifetime. But for a mobile phone, we do not want the same lifetime. We do not expect a mobile phone to be operating 20, 30 years, because a new generation will come, new software will come, better technology will come. So we can say that we have different scenarios in terms of expected reliability. But when we talk about the fundamental things, and that is power electronics, I would say that we have two phases, and this can be even more detailed, which is illustrated by years up top here. We have before 57, and then we have after 57, where I would say the modern power electronics was created. Before 57, we were using mercury arc rectifier, vacuum tube rectifier to do some functionalities which were good, and we could do many exciting things. But by the invention of the thyristor, where we by a simple turn-on circuit could turn a thyristor on, and it can conduct, this was an amazing development. I know we need an external component to ensure that we can turn the thyristor off, but this was really a landmark invention that we were able to do this. That was in 57, so this is more than 60 years ago. And for a long time, this was dominating. So, but in the mid-70s, we got the first devices. That was the devices where we both could turn on and turn off as a force commutator to turn off. And that was first the bipolar transistor, power bipolar transistor, and then it became the power MOSFET, which, of course, you know. In the 80s, the IGBT came, which was a combination of the two devices I mentioned before. And then in the 2000s, what I would call the next, really generation of devices was coming, not necessarily with a lot of new innovations in the circuits, but the devices themselves were changing fundamental material from silicon to silicon carbide or gallium nitride, also the wide bandgap devices, where we first got the diode around 2000. And now we can see a lot of devices coming where, if we look at the performance, that's fantastic performance we see there. So we have a phase one where it's we just look after better and better switches. We have a phase two where we look at switching times, losses, power density, cost, roughness, as make them better and better, temperature range, and as well as controllability. If we look at the power electronics part, before we were limited by how the switches could do. So there did not come so much out of it. It was non-linear elements. We could apply it in different applications. But after 57, then new circuit topologies was coming. We did new modeling methods. We did improved control. And then everything was moving on as the devices become better and better. And late in this period, which I will call phase two, the digital control also come into play, and we could do many fancy things. And then after, with the wide bandgap devices introduction, we do not really see some very new topologies. What we instead see is the development of many applications, and we are, let's say, optimizing everything according to that. And that includes thermal management, EMI, EMC, packaging, big systems, modularization, and also reliability, because we want certain reliability dependent on the application. So that is also one of the reasons I think that reliability in the last 10, 20 years have been more on the agenda, also in the academic society. So if we talk about power electronics, we can say there are many things which, when we do design, and what is the expectation when we are using it as a cheaper, lighter, smaller, cooler, more reliable, more versatile. When we do the design is something to do with cost, power density, efficiency, control, input, output, performance, and of course also reliability. And one example just showing the trend is this chart here. This is one I have here today. And we can do this today with gallium nitride components. And this is complete showing that things are moving into more power density, higher efficiency, because we could not have this power density without having a higher efficiency and so on. So this is really moving on. And we are applying power electronics in many applications, and we see emerging activities. One is what we call electrification of the transportation, where a change is going from, so typically we have an AC, and then we have a low frequency transformer, and then a converter to do the traction. And the alternative, which is really coming up now, is that, okay, we still connect to the high voltage, but then we have what we will call a medium frequency transformer, and in that way, really compressing the size, but still stay connected to the high voltage size. And this is an example where we really can squeeze the size by more advanced power electronics. And if we look at a whole train system, which is illustrated here, here you have the traction system I showed before, but we also need a lot of other power electronics for doing different things. One is also to supply inside the in the train, and you can see we see DC AC, we see AC DC, DC DC to support cooling system, emergency system, battery systems, and so on and so on. So we really see power electronics being entering into many parts of a train system. And here are some examples from two companies. One is ABB, where you have this high frequency transformer system, where you go in a series connection of 3.6 kilovolt of devices and put them in series in cells, and then you do DC to DC conversion, and then you have the DC for driving the car. So this is one example where we see really emerging technology being developed. Another example is in 2014, Mitsubishi, they did a full silicon carbide traction inverter, where it turned out that it was possible to squeeze the inverter size significantly by introducing new technology. And here, the topologies which have been applied is no, but we are applying the components which have been developed, and we get much better performance out of those systems. Another area is renewable generation in general. We have in 2018 installed 1,000 gigawatts, so that means today maybe 1,200 gigawatts. That's a lot, also, to be honest. And in renewable generation, for example, in wind turbines, but also in PV, we have, of course, a lot of power electronics. We have the blades, we have a gearbox, we have a generator, then we have AC to DC, DC to AC conversion to connect to the grid. And what is really important there is efficiency, cost, volume. It's the ability to control in different ways, including also to have a high reliability and secure that the supply is really like it should be. And in general, we can say what is really make things happening in the renewable generation technology is the power electronics. If that was not there, we were not able to do anything. And this is a key technology. Also in PV, we have, of course, applied a lot of power electronics, but I want here to illustrate with this one here that the reliability of the systems are important. So here are 3,600 statistics on 3,600 service tickets on a lot of systems over more than 2 years. And the question is, where are the failures in a PV system? And you see here, where are the failures? Where are the tickets coming from? And also, what is the cost implication? What are we losing of energy? And you can see the inverter is far the most components which are failing. So this is worth to look at. And yeah, the root cause is different places, but especially parts and materials are the reason. So that means the inverter components themselves are not good enough. And it turned out in this statistics that 50% of all lost energy production is just because of 5% of the incidents. So if we can attack those and improve those 5% of incidents and improve them, then the situation will be better in terms of those metrics. And another example seen from the field is the wind turbine. Also here we have 350 onshore wind turbines operating for a lot of hours or years, and there have been downtime events. And where do they come from? And you can see here some statistics on the faults where they're coming from, and 13% are coming because of the power electronics. And of course, there are also other things which can go wrong in a wind turbine system. It's seen from a system perspective, a much more complicated system with a lot of rotating things. But the implication, if the power converter fails on the cost in terms of the downtime, the power converter accounts for around 20%. So it really matters if they are failing, and it matters if we give them, make them with a high reliability. So here is an illustration. What does it matter in terms of cost of energy for renewable generation? And in this case, it's a wind farm system. So if we are going to go on a site and want to calculate what is the cost of energy, what really matters? So we can go in one area, and that is the price of the turbines. It's also the lifetime. It's the cost to rent, to get the capital. So in that way, we get some amounts which we are calling the capital cost per year. So for sure, that has something to do. On the other side, when we look at what we get out of it, this has something to do with diameter, hop height, and so on. Plus, of course, the surroundings, mean wind speed, site characteristics, and in that way, we can calculate the kilowatt hour. But what is also coming in this figure is that the operation and maintenance cost is important and being taken into account. So we have to calculate that in order to get the total cost per year. And we can say if we have failures, then the operational and maintenance cost will be higher, and also we will get less annual energy production. So the risk of having a poor reliability in such system is both in the nominator and in the denominator in terms of calculating what is the cost of energy per kilowatt hour. The reliability issues in power electronics, of course, this has been a steady progress, and what we can say is that there has been a past history. There is a present history, and then there is what we will call the ambition for the future in terms of reliability engineering in power electronics. And of course, we can look from different sides, from the customer side, from a manufacturer side, what is the reliability target, how do we approach it, seen from an R&D side, and also how are we doing the analysis in terms of tools we are applying. Now I will not go through everything, but in the past the affordable return rates was okay. But today, because the margins are so low, or we want to have we want to have good surplus, then in many applications, we just want parts per million return rates. We really want to understand the product, the load, and so on, and then be able to say something about this. Also, the customer wants totally peace of mind, and just things are operating. And in order to ensure that, we can say we have to understand the load, we have to design for a certain reliability, we have to understand why things are failing, we have to explain it, and in order to do the design, we are not only designing according to some electricity performance, we also have to look at thermal performance, we have to look at other aspects in the design in order to be able to do what we can call design for reliability. And in that context, when we talk about peace of mind, we need predictive maintenance, also that means more intelligence put into the products. And if you are a component supplier or you are a system supplier, for example, a wind turbine supplier, you can say that, okay, you can sell a product, but you could also sell a service where the customer do have peace of mind. And then you as a manufacturer also delivering the service and get money for that. And in order to do that, you need data in order to do monitoring. And of course, all the time, based on the data, analyze what's going on. And that means also know a lot about the physics behind failure. And I would say this is the new paradigm in a lot of business, that the customers have peace of mind, and then you both do the service and you come with the product. And many companies are earning a lot of money on the service also. So if we look at, for example, design for reliability, we have to look at how long time should such systems operate. And you can see here 6 different applications. And here I have estimated how long time we expect them to operate. And you can see they are very different. So it really matters that we are designing according to those lifetimes, expected lifetime. So we have cars, which are maybe 10,000 operating hours. And then we have renewables, which we expect to operate, let's say 120,000 hours. And it should be as cost efficient as possible. So there is a huge range of lifetime targets in power electronic applications. What does it mean if we are not doing it well, seen from a manufacturer perspective? So if you are going to design a PV inverter or converter for a car or something like that, the way it typically works is that first you do a concept. This is where you draw some circuits on a piece of paper. You are okay, it seems to be okay. Then you do a design. Then you spend 10 times more money. Okay, still okay, you feel comfortable. Then you go into a validation phase where you do a prototype. Then you spend 100 times more. And after that, you launch it, put it into production, set everything up. You spend at least 1,000 times more than in the concept phase. But if you then realize that when it is in the market, that after just 2 months things are failing, then you are losing a lot of money. You have lost all, you can easily lose the money illustrated here, and maybe even more, because you're also losing reputation and so on. So it's really, really dangerous if you are not very careful in that. And the homework done in the concept and in the design phase are given a lot of value for you, so you can avoid those things. And that is the reason we say design for reliability. And yeah, it has something to do with culture in terms of design and mindset and so on. And here I have taken one example from the mobile phone industry, and where we would say poor reliability comes into play. So there was issues with Note 7 Galaxy, where 96% of around 3 million mobile phones were returned, and they had to investigate a lot, and they lost around $5 billion of income because of that. And the main reason was that the design of the battery was not done properly, and especially the manufacturing of them was not done properly. And that was something which could have been catched if there was have been good testing processes, and there have been good design for reliability. Okay, so let me just stroll a little bit around what are the challenges in the power electronics reliability thing. And first of all, what is reliability? And let me define that here, saying that this is the probability that an item can do a function under certain conditions in a given interval, a given time interval. And the lifetime, this is the time from initial operation until failure, okay? And then we have something we call percentile lifetime, and that is given according to a certain population. So if we say we have a B10 lifetime, that means the time until when 10% of them have been failed. So if we have B50 lifetime, then 50% of them are expected to fail. And this is illustrated a little bit here on this curve, where fundamentally you have 2 subsystems, A and B, and they have each of them have a certain reliability as a function of time, and you can see they are different. Then they are put in series. If one fails, the whole system fails, and then we have this characteristic here. And what you can see then is the B10, B20 lifetime. So in this case here, we expect 10% to be failed after around 600 hours, and in this case 20% are failed after 1,000 hours or something like that. So what is reliability engineering? This is many things, but in general we can say, because we are so good to design things, that what is really happening in terms of reliability is that we have to design our system to be strong enough to survive or to operate a certain load over time. So what is illustrated here is a little bit the load distribution of an application. That could be the generation from a PV. And of course, we have a peak load, what we call an extreme load. Then we design a converter, and it should be stronger. It should be able to manage the load. And in all aspects, taking all uncertainties into account, it should be stronger than the load. So this could have a distribution like this. This is in Italy when we have done the design. Then after 5-10 years, the components, they become weaker. So what will happen is that the strength of the system you have will be weaker. This will be less, while we can expect the load to be around the same. So that means this one here is moving a little bit to the left, and dependent on your load and your design, you will have a little bit overlap here. And then in the case that the load is very high, then the system can fail. Some systems can fail of a population. And then after a longer time, you can see that we have a bigger overlap, and then we would have more failures. And then the question is, okay, seen from a manufacturer perspective, let's say after 20 years, do you want to see 20% failing after 20 years, or do you want to have 5% failing, or whatsoever? And this is designed for reliability, to be able to say something about that. And the reason we see this is, of course, that there are degradation components are wearing out. So in order to find out what is this, then we have to understand the load, like you saw on the previous diagram. So this is also what we in many cases call mission profile. And here are shown some examples of a little bit extreme cases. What you see here is temperature in Arizona, so you can see how frequent you see that. So you see here very high temperatures, you have to deal with that. You also have a relatively dry system in Arizona, but you also have to take into account severe users. How are they going to do the loading of the system? And you also have to take into account severe environment, water, snow. It can also be dust, it can be sand, and so on. So you have all the time to think about what kind of environment are we putting in the power electronic system. So how to deal with this when we are dealing with a system? So let's say we do a system for a certain specification. So in order to analyze this, the way we are doing it is that we look at the application, and we do design and so on. And then we can say we have three special areas where we have to have special attention. One is the hardware, second is the software, and the third is human errors, and how to avoid that human errors is happening. But it can happen, and maybe you should be able to take this into account. And in terms of hardware, we can fundamentally have wear out, and then we can have catastrophic issues. The diagram you saw before with that the strength was becoming less and less. This is especially when we have wear out of components. So what we do then is we have semiconductors, we have passive components, we have other components. All of them we try to characterize and see what are the loading according to the application. And then component for component, we come up with a reliability expectation, and then we put them all together in order to be able to say something about the reliability and the strength of a certain product. So that are transistors, diodes, magnetics, caps, PCBs, gate drivers, fuses, and there can maybe be added more. And then the same thing you have to say about software, and you also have to say a little bit about what are the probability that some human errors will come. So how to deal with this? Okay, what we do typically is we try to understand what we call the mission profile, the conditions where the equipment is in. Then we have the system, like I showed before, machine, converter, topology. So then we analyze at system level, where we put up models in terms of describing what is going on. We get temperature, current, and so on. Then we look at each component. What do they see of current? What do they see of voltage? What do they see maybe of temperature? What then comes out of it is voltage, temperature, maybe relative humidity. Then we analyze the reliability of each component, put that into, get some reliability metrics, put them into a reliability block diagram, and then we have the final system reliability and can say something about the expected failure rate during time when they see a certain emission profile. There we also get information out of many other things, components and so on. So this is a typical way to assess it and do the work. So when we talk about power electronics reliability, we typically say we are dealing with three main things. We are dealing with physics, the analytical physics, say something about the components, say something about the physics of failure in the components when they see certain loads. This is one area. Second area is the design and verification, including how to design so we have a certain reliability, also how to validate, how to test a certain design so we are sure that it has the robustness we want it to have from the beginning. So we after 20 years, for example, see only, let's say, 5% failures of the converter we have done. And then we can also say when we are in operation, control is something which can increase our reliability, as well as monitoring different parameters, for example, condition monitoring, in order to be sure that we are not doing something which is really damaging the system. So what we say is that the reliability engineering is going from components to describing the failure mechanism. So, and we are going from constant failure rate to failure level with time, like I illustrated on this figure, and also from reliability prediction to robustness validation to be sure it's robust enough according to it. And those things here are taken from microelectronics reliability. So then I have some examples about this, which I will stroll through. One is, of course, to understand the component level degradation. And there are different ways to do this through testing, through simulation, and also through condition monitoring. And here is one where we, by what we call multiphysics simulation, we are not only simulating the power losses, but we are also looking at the temperature. Then we we need to take into account the physical mechanics going on, because we typically have temperature difference between different layers. When we know something about this, then we also can say something about what is the expected lifetime. And typically what is wearing out and degrades such kind of systems are that the temperature goes up and down, and this way you often do this. So here we have temperatures variation between 100 and 140 degrees on diodes and on transistors. So this is something which is really moving on in a fast pace. So we better and better, for example, can simulate a plate like this where there are 4 silicon dies. In order to understand the degradation, we also need to test a lot. And one way to do this is to stress electrically and thereby thermally devices. And here we have a test system for doing this, where this one is IDBT system on the test, and then we have a loading system here at this side, and then we have power circulating between here, and then we can let the temperature go up and down. And here's an example of such kind of test system. And then we can explore many different things. One thing we could explore is the number of cycles as a function of the cycle time. And this is illustrated here. So you can see as the cycle time becomes shorter and shorter, then the number of cycles the system here can withstand become higher. So this means a lot. whether you run with 5-second cycles or 10-second cycles or 15-second cycles for this module. Another thing which we also can investigate and monitor is when we do this way out, we load the system heavily, we can monitor the collector emitter voltage. And if that is changing, then something is also changing in the module. And this is illustrated here where you have millions of cycles at a certain degree. And in the beginning, there's no change. And then after some time, we see some accelerated change. And that is because bond wires are lifting off. And then suddenly we also are moving into a catastrophic failure. The same is interesting for capacitors. As I told you, we don't only have semiconductors. So what is illustrated here is the degradation of film capacitors. Here you have the same caps, but you see here the capacitance value during time, where they are loaded with 85 degrees C and with 55% relative humidity. Try to look here how big variation there are between the capacitors, even though it's the same capacitor. So that is also saying that when you are modeling those components here, you really have to take the variation into account in order to say something about the probability that certain components will fail. And in order to understand what then is going on, what has happened, for example, because we have such kind of reduction of capacitance, then it's a very good idea to study in more big details what has happened inside the devices. Also, in order to understand the degradation, we can do other things. One is to monitor the peak current in the gates when we turn an IGBT on, because it turns out that the peak current we are seeing in the gate is dependent on the chip temperature. So this is illustrated here where we have different chip temperatures, and then you can see the current, and you can see there are some dependency of temperature, and then we can use that for saying something is the device moving towards being overloaded, and then we can say we are coming maybe closer and closer to a failure. Another thing which could be interesting to monitor is the remaining lifetime of capacitors. And there, for example, you can have a neural network to model based on, let's say, certain input parameters, what is the expected capacitor value, and in that way be able to say something about if the capacitance is going more and more towards the final wear out. Okay, so this is more on the component level. Then we can move up to system level. And for example, how do we analyze this in big detail? And here is shown one example. This is a modular multi-level converter. You can see you have a lot of components. You have one module by one module here, and we put them in series and see how they operate. We try to apply them functionality-wise by doing a prototype. And in this prototype, which is of course downscale compared with a very big system, we have the ability also to monitor the junction temperature on the chip surface and so on. So this is just to validate what we are doing. And what we typically do in order to analyze a system like this with an MMC is that, and we are applying it, for example, in a wind turbine, then we look at what is the wind speed. We try to say something about how the power conversion is going on. Then we have a loss model, we have a thermal model, then we do some, based on the thermal model, we have we do some counting of how many cycles we see. And based on the cycles, we say something about the lifetime. But in order to take into account the variation, we do Monte Carlo analysis in order to get a lifetime distribution. And then we can say something about what is the expected lifetime. So the question is, of course, there, how much data do we need to have in order to say something qualified about the lifetime of, for example, this MMC converter? And there we, for example, can have 1 hour between each data. We can have 10 minutes of each data. We can have 1 second of each data for the wind speed, and then do the analysis of an offshore HVDC converter station where in a wind farm here. And yeah, then we generate the wind speeds and at a different resolution, and we have our power converter model, and then do the calculation of this converter. What is the wear out of and degradation of the system when we do this, using different resolutions. And here you can see numbers for different components in this MMC converter. And then you can see for 1 hour, you can see down to 1 second. And you can see here for 1 second compared with 1 hour, there is a very, very big variation. So the message here is that we should be very, very careful not to have too rough resolution when we do this analysis. Otherwise, we will get a very, very big surprise. What you can see here is a measured temperature in the chip when the current goes up and down, and this measured temperature we are using for validation of the system. Okay, so let me just, the time is running relatively fast, and there should also be time for question. But what can also move on in the thinking when we say something about design for reliability is that if components are too sensitive or they are hard to be applied, then maybe we have to think alternative to come up with new components which have a higher reliability. And one of the fragile components are the capacitors, especially the electrolytic capacitors, and also the film capacitors, and sometimes when they see humidity. So in an application where we have a system like this, we have the AC, we have the DC, typically we have a double line frequency current in a converter like this. And what we want to do there is to, we can use a capacitor in order to smooth that out, or we can also apply what we have been working with in the past years, what we call an active capacitor. So where we have the same number of terminals like a capacitance, but then we are applying active switches, passive components, as well as control in order to emulate what a capacitor typically will do. And this is really illustrated here. The fundamental idea is for this electronic capacitor or two-terminal active capacitor is that, if we have a DC link, then we have a small capacitor which takes care of the main DC voltage, and then we have another capacitor which is controlled by a power converter, which is emulating the AC part of the capacitor, and then control. Of course, because it's two-terminal, it has to be able also to supply the power to itself. So the performance is illustrated here, where fundamentally we have applied 110 microfarad capacitance, and we try to emulate 1100 microfarad capacitance by this circuit here. And the characteristics of a 110 microfarad capacitor can be seen here. The characteristic of a 1.1 millifarad capacitor can be seen here. And there you see the characteristic of this two-terminal active capacitance, that when we come to a certain frequency, we can exactly by this low capacitance emulate a 10 times bigger capacitance, and in that way get the same performance. And this is illustrated here, that we can shrink the size and at the same time get very, very strong performance, as well as the capacitance has been changed from being electrolytic to a film capacitor. Okay, the second last application in terms of what we can work with here is also to do the design, because we do design, we also need tools in order to do that. And we have been working with that for a couple of years now, where the fundamental idea is, of course, to simulate in very big details, but then with some model reduction techniques, we should be able to analyze complicated systems, so system engineering approaches. So we have done a tool where both we can do ANSYS, combine ANSYS and Plex simulation, where models are fed into what we call a DFR2 tool, and then we can come up with specific characteristics in terms of reliability of the components. So it's a tool where we can specify the mission profile, we can do system level analysis, we can do system circuit simulation, we can mission profile analyze each component. When we have done this, then we can say something about their component reliability, and then we can put everything together and then say something about the system level reliability. And the tool we have done enables us to also put data. We don't have to do the whole process flow. We can just go in at a certain places, and then we can do the analysis. And this is also illustrated up here, that this is the user interface for the people who are applying it. So here's one example of the user interface. You will see this is for a PV panel where you have the environment, you have the panel, you have the power states, you have the components inside. And then we can say what are the grid codes and so on. And then we can analyze at component level, we can analyze at system level, and give the total system reliability for a given location. And such tool we continuously are increasing in terms of performance. I think this is really a must if we want to design for reliability. The last thing I will just say is that we have also developed something in the condition monitoring area, where the fundamental idea is in a smart way to monitor the on state of the components in a power converter without in a simplified way, and use this information to say something about what is the health, what is the state of health for this converter. And this we have developed here. You can see how the voltage looks like across the devices, how the operation is of a single phase inverter. So what we have developed is a very simple circuit where we can, in a simple way, measure the collector emitter voltage across the different components in an inverter like this, and be able to say something about what is the health of state of the converter. So we have done a system where we just connect here and here, and then we can say something about how the circuit is progressing. And here is the converter, and then this small print circuit board can, in a very simplified way, which is illustrated here, measure the collector emitter voltage across the devices we are applying, and with that come with some prognosis about how the system is operating, and also be able to detect or predict failures which we otherwise will not be able to detect. Okay, so let me give a summary of this presentation this evening. So I have touched what we mean by design for reliability, power electronics reliability. This is in a much more detailed way to understand the physics, the reason for failure, the physics in the component, so we can explain what's going on. This is to design converters where we take into account the reliability of the components. When we have done that, of course, also build and prototype it and say something about the robustness. In the field, when things are operating, then control can make a very big difference to ensure high reliability, as well as the condition monitoring is a very big possibility for us. And then tools are necessary in order to, as a simulation tools is necessary at different levels to master this. We have to do validation in practice also in order to be sure our design are according to the specification. And then if the reliability is not good enough of the components we are applying, we can look at to develop the next generation of components, which gives us a very big flexibility and also hopefully a higher reliability. So just books in the area, there are books in the area. We did some years ago one reliability book, which in many ways defines some of the things we have been working with. And hopefully in the future, in a few years, maybe we can update this one as we come further. So that ends my presentation this evening, and as promised, I will be very happy to answer questions, and thank you very much for your attention. So the floor is yours.
Thank you, Professor Blaabjerg, for the very enlightening session on reliability of power electronic systems. Now it's time for Q&A. We have plenty of questions in the chat box, Professor. So shall we take a few questions now?
Yes.
Okay, over to Eldo. Eldo, please read out the questions.
Yeah, sure, sir. And by the time there is feedback form has been shared in the chat box, participants do fill that also. So we do have around 5 to 6 questions in the chat box. I will read them
Yes.
out.
Yeah.
I would like to know if there is any reference journal paper that demonstrates the calculation of reliability or related calculation, preferably for a simple power electronic converter. This will enable someone to start from scratch on understanding the mathematical part of reliability and associated calculations. Question from Rakesh Kumar.
Yes, there are. I think maybe the most efficient way is that I send this presentation to one of you, and then I give also some references. In the presentation here, we have listed some different references where some of them are a good platform for it, but there are a few others maybe I would like to highlight. So I will send that. I think that's the most efficient way, because just to mention here is it's not so precise, if we can say so. So I will send the list.
Thank you, sir. Next question. What is the role of power electronic components qualities in terms of designing power electronic system? How can we assure the quality of components?
Well, that is a good question, and if you talk with manufacturers of electronic products, for example, power electronic products, they have to specify to their suppliers of components that the components they get, they have a certain maximum variation, if we can say so, and also they have a certain quality. So this will fundamentally be the way of ensuring that the quality is okay. So there is a big, let's say, data tracking responsibility, both for the supplier side and also for the company who is manufacturing the converter.
Thank you, sir.
But it's very, very relevant, because if the variation is big, I don't know if you recall the diagram where we have measured the lifetime of the capacitance. I would say if we put this capacitance, let's see, I'm soon there. If you see this one here, this is the same cap, and you can see the huge difference, right? So one is very good, where the capacitance value has just decreased a little bit, while this one here, you will have a failure very fast, because so here the quality is not good enough.
Thank you, sir. The next question from Krish Mishra. Sir, could you also tell the effect of parasitics and capacitor ESR on the reliability of system and the solution to it?
Yeah, in terms of ESR, ESR is a good this is a good indicator of remaining useful life. So if the ESR is increasing, for example in a cap, then the losses will be bigger. If the losses become bigger, then the temperature become higher, and in that way you have, let's say, a negative or positive loop, depending on how you look at it. But the point is that then the lifetime will decrease very fast, and it will fail. So ESR is a very good indicator for lifetime, no doubt about this.
Thank you, sir. Next question from Sanida. Is there any provision for outside researchers to utilize the DFR2 application? And is there any provision to get early emission profile data at Denmark location? Solar
if we talk as a mission profile, can be different things. As a mission profile, it can be wind speed, right? It can be solar irradiation. such kind of data, if you, let's say, Google data or something like that, they are available also in what we can call open access form. If we talk about mission profile for motor drive in a fan application, sometimes you maybe have to assume something. If we talk about mission profile for car, then you know there are different driving cycles, and they are defined there. So yes, there are open access mission profiles in different areas, and in other areas they are defined by standards, and in some areas you have to assume something in order to have the mission profile.
Thank you, sir. Next question. What issues do we face in bidirectional converters used in decentralized distribution system and the approach towards resolving them?
Oh, can you repeat it? So you say a question about bidirectional power converters,
Yeah.
right?
Converters used in decentralized system.
Yeah, so bidirectional power conversion we use in different applications. For example, in cars, right? Also where you have to charge and discharge the batteries on board, right? This is an obvious place. Also, if you want power to go back to batteries, if you are braking. While if you take application like PV, there you want the power to go out from the PV panel. If you take the wind turbine, you also just want the power to go out from the generator. But especially in battery as a storage application, and in application where you have to recover energy, for example, through braking or something like that. These are applications of bidirectional power, and of course also solid state transformer, as where it can be very interesting to have bidirectional power.
Thank you, sir. Next question. Did they include ESR while designing active capacitor? How to take this into account while designing?
We want to avoid to have any ESR influence. But what we can do, if you look at this topology, so we of course have so there is a small ESR here, and then we of course also have an ESR here, but because it's relatively low, we do not expect that to have and there's also an ESR here, by the way. But because it's more low voltage, it's not so dominated. But of course, during a long lifetime, which we expect this one to have, we also have to be aware of whether the ESR is going up, and then be able to say if some failures are happening. But the topology here should have a much lower ESR compared with, let's say, a conventional electrolytic capacitor, and especially when time is going, because the electrolytic capacitor will wear out. But it's a very relevant question, absolutely, very relevant. So every time you have a capacitor, you will have a kind of ESR you have to deal with. So it's very relevant.
Thank you, sir. Next question. Is reliability parameters based on number of levels for multi-level inverters?
Yes, so you will absolute in the last you absolute. So if you take this multi-level converter, yeah, also when we do the reliability calculation, finally we look at can we accept, for example, that one of those are failing and then still operate the system. Okay, so this is n-1, and typically we say that we need to have a system where that's the case. And then we are also able, because we have characterized them We have developed a model for them one by one. And then at last, when we do the reliability block diagram and the calculation, we will be able to take into account whether we can operate still with n-1 as a means one fail, or maybe even we have accepted to operate with n-2, because we don't want this one here to fail at all, and maybe also have the possibility in operation to change on the fly the module so they can come back in operation without shutting down the system. So yes, we are able to by method to take that into account. And this is also a little bit designed for reliability, right? If you want to have the option to operate with 2 or 3 non-operating modules, or just 1 or 0, and then you make decision about how reliable the system should be.
Yes, sir.
Eldo, 1 second. So thank you, Professor. We have a few more questions coming, but we are 10 minutes above our scheduled time. So what should we do? Shall we take the questions later via mail? Or
take 1 or 2 more. Take 1 or 2 more. It's up to you.
Okay. Okay. So Eldo, you can read out 1 or 2 questions.
Yeah, sure.
Sure.
Yeah.
Let's wait with some questions. That's very relevant. That's engineering.
Yes. Yeah. Do I need to take into account the various switching harmonics or power level harmonics in DC currently while designing a DC bus capacitor for an inverter?
Oh yeah. So you have to analyze the current ripples, and because the losses typically are frequency dependent, so you have to map that as either by simulation or by analytical formulas, and calculate what are the ripple you see in the capacitor, and in that way look at the losses. Otherwise, it can it depends on the caps, but it's a very good idea to map the harmonic components and then calculate what are the expected losses in the caps. Absolutely.
Thank you, sir. Next question. In practical situation, how much time in advance the failure of the converter can be detected?
Oh, that's a good question. Well, I think it depends a little bit on the failure types. So I would say, I illustrate here, for example, that was the wrong way. For example, if you monitor the collector emitter voltage, this is what we show here, right? This is number of cycles, 1 million, 2 million, 3 million, 4 million. And you can see here you see nothing, right? You see nothing. But here, as you have an increase of, let's say, and this is delta. So you have an increase from 0 to 20 millivolt, let's say. So here I would say you should be able to say, okay, now I'm coming closer to a failure. And then you can say you have from 4.5 million to 5 million cycles, and then you go into failure mode. So in this case, we can with relatively high probability, let's say, if the lifetime is 20 years, then we can with relatively high probability say that this could be said months before, so that we were moving into that direction. But that's maybe, this is just, it could also be 1 year, and then 20% before failure, we could say it, so then it's a shorter time. But of course, there is a risk that there are some variation here also. So seen from a statistical perspective, some of them could maybe do faster. So in order to have a certain band of safety, you would maybe say before that this is needed to shut down before.
Thank you, sir. Sir, shall we continue, or can we take
the next question can be the last question, that condition monitoring, that question.
Yeah.
Okay.
Sure, sir.
Okay.
Does condition monitoring and reliability of power electronic components used in power electronic intensive cyber physical microgrids also influence cyber attack identification indices derived from monitoring these quantities? How can we differentiate system fault from cyber intrusion in that case?
Oh, that's a complete other area. And the cyber security and attacking, let's say, signals and so on, and put up robust, let's say, cyber physical models, so we are able to detect it. This is not something I have done a lot on, but there are publications today which are discussing that you can have a parallel model of your system, and then if you see some deviations between this parallel model and how the system is behaving, then there is a high probability that you have a cyber attack and you do not have a hardware failure. But of course, this is an important domain of discussion, because but anyway, we can see there is a failure, but it's very important to be able to differentiate between those two different failure types. And I would say, if you look at the diagram I showed in the beginning, where you have software, you have severe user, and then you have the hardware wear out or something like that, then this is a combination of hardware and software. So some kind of cyber physical models are important to include into your control and monitoring in order to be able to identify cyber attacks.
So, thank you, Professor, for taking all the questions. Next, I invite Bijana Madam for the concluding remarks and the formal vote of thanks. Bijana Madam.
I don't know. This is the best presentation that I have attended for I don't know how many years over. Thank you very much, sir, for being so actively participating and interacting with the questions also. Indeed, it was really eye-opening for us, and you gave us the minute details of everything that we really value the presentation that you have made and the question and answer session. Thanks to the participants also who raised such wonderful questions. Thank you, Professor Blaabjerg. Thank you very much for being with us for so much time and sparing us. And we do look forward to have your physical presence also once everything comes back to the normal. And we welcome you to Kerala. Thank you very much, sir.
Thank you very much for the words, and thank you for the opportunity to talk for your chapter. I wish you the very best for the development of the chapter, recruiting members, work with members, so they can continue a positive career.
Thank you, sir. Thank you.
Thank you very much. Thank you very much.